All right, let's turn on power.
Hello, my name is Grant, and this is my autonomous robot that I made for ENPM 701 at the University of Maryland. I built it to complete the Grand Challenge at the end of the course, which consists of autonomously retrieving 9 blocks in the correct order by color and bringing them to a destination. Within a square arena, the robot must start in one corner, find all the blocks on the far side of the arena, and bring all the blocks to the adjacent corner from the starting point. This clip shows the robot doing the challenge on a smaller scale with just 3 blocks in my home. Building this robot from scratch and getting it to successfully retrieve all of the blocks has been a huge challenge and a lot of fun. In this video, I'll walk you through my experience and detail some of the challenges that I ran into along the way. 14 weeks ago, I began with a pile of parts. The brain is a Raspberry Pi 3B Plus running Raspberry Pi OS Bookworm, which is the latest version. The main structure and the motors of the robot actually come from a kit from DF Robot. The primary sensor is a camera on the front, but it also has encoders on 2 of the motors for measuring distance traveled, and an ultrasonic sensor for measuring distance to objects in front of it. And of course it has a nice big gripper on the front in order to pick things up. After construction, it was time to test that everything was hooked up correctly. Here we can see the motors turning, and here we can see the very first time the gripper picked up a block. Concurrently with construction, I worked on getting the basic computer vision working. The vision algorithms aren't particularly sophisticated. They primarily consist of finding a hue saturation value, or HSV threshold, for each of the colors of the blocks that the robot needs to pick up, and applying that threshold to the camera feed. From there, we can find the object we're looking for and estimate where it is based on its size and position within the frame. I developed a small program for finding the HSV threshold values on a live video feed from the camera. Here's me testing it on an Arrow on my phone, and here's me using it later in the Grand Challenge arena to find the HSV thresholds for the blocks themselves. Next up was getting the fundamental movements working. Precisely and quickly moving forward, backward, and pivoting left and right were critical for the robot to be able to navigate the arena and find the blocks. In particular, pivoting proved difficult, and you'll notice that in this video. The robot kit is set up to use skid steering for turning. That means that the wheels don't actually turn themselves, and instead they need to be able to skid on the surface that the robot is on. That means that the motors need to be strong enough to overcome any friction between the tires and the floor in order to turn. In these early videos, you can see that the pivoting barely works. The tire dug into the floor, and the wheel dug into the body of the robot. The motors just weren't strong enough to overcome this by brute force to turn. I addressed this in 3 ways. I added masking tape to the wheels, which reduced friction. I added thrust bearings between the wheels and the body. And most importantly, I used a proportional controller with a pretty high p-value, and that was based on the feedback from the wheel encoders. This ensured that each side of the robot ended up turning the same amount. This results in a sort of wiggling motion, which helps free up each side of the robot when wheels start to get stuck. After I got basic movement down, it was time to integrate an IMU for more precise control. Here's the data feed that I get from the Bosch IMU. It does all of the sensor fusion on board and gives the robot absolute roll, pitch, and yaw values in degrees. Here's the robot traveling in a pretty accurate rectangle by using the IMU to turn almost exactly 90 degrees at each corner. In addition to allowing the robot to stop pivoting at a precise angle, the IMU is also the measurement used in the proportional controller to make the robot move in a straight line. By combining the new, more accurate turning from the IMU with the block sensing computer vision, I got the robot to start pivoting towards the block as it moves around. And finally, putting everything together, the robot traveled to and picked up a block all by itself for the first time. Now that all the pieces worked and I had that initial success of picking up a block, it was time to integrate all of the functionality into one program that could explore the Grand Challenge Arena, find all the blocks, and bring them to their destination. This is also right around when I got access to practice in the actual arena, so while I describe the overall algorithm, here are a bunch of sped up test runs from the perspective of the robot, including mostly failures and even some crashes. The algorithm is a state machine. You can see the state in the top left corner of each video. The robot begins in the scan state. In this state, the robot rotates 15 degrees and takes a picture to look for a block. If it doesn't find one after rotating a total of 105 degrees, then it goes to the center of the arena and starts scanning a full 180 degrees in the same fashion. When it does find a block, then it goes to the orient state. In the orient state, it takes a picture of the block and creates a bounding circle. It measures the distance of the center of the circle to the center of the robot's view, and from that calculates an estimated angle to turn. After pivoting for that angle, it decides if its orientation is close enough or if it needs to do it again to get closer. If it's close enough, then it enters the approach state. In the approach state, it calculates a bounding rectangle around the block. From the width of that rectangle, it estimates the distance to the block. The function of width to distance was determined by taking experimental measurements and deriving a function from them. For my particular robot's camera setup, the function was the distance in meters is equal to 25 divided by the width in pixels, and that was good enough for this application. But because there is some error in the distance calculation, as well as the orientation from the previous step, the robot only goes about half as far as the calculated distance. It then re-enters the orient state. If the estimated distance is less than a threshold, then it opens the gripper and enters the grab state. In the grab state, it moves forward one last time and closes the gripper. Then, to make sure it was a successful grab, it takes a picture before and after reversing for 10 centimeters. If the width of the block in the camera view hasn't changed above a certain threshold, then the robot assumes it was a successful grab. If it wasn't a successful grab, it re-enters the approach state, but if it was successful, then it enters a return state. Now, this whole time, the robot has been keeping a detailed history of how far it has traveled and in which direction, so it knows where it is in the arena. In the return state, it calculates the angle to turn and the distance to travel in order to go to the destination for the block, and it does that. This only works because of the amount of time I spent making sure that the fundamental movements of moving forward and reverse and pivoting were very accurate. After dropping the block, the robot backs up, then goes to the corner of the drop-off zone and re-enters the scan state to do it all again until it has retrieved all 9 blocks. Now, after lots of practice to work out the bugs, it was time for the robot to complete the challenge. Here you can see an overhead view of the robot successfully bringing all 9 blocks to their destination. The point of view of the robot is shown at the bottom left, and next to it is the map of where the robot traveled over the course of the challenge. It took about 6.5 minutes to complete, but this video is sped up to show the whole run in under a minute. One of the defining characteristics of my robot that I'm proud of is how smoothly it moves. Part of making the fundamental movements so precise, as mentioned earlier, was having the robot smoothly accelerate and decelerate through all movements. In this project, I gained experience with the fundamentals of building a robot and integrating the different subsystems together to achieve a high-level task. And in the end, it was exciting and gratifying to watch my robot successfully complete the challenge. And it was fun.